So greetings to whoever is watching this video. My name is Shun from Management and Science University in Shah Alam, Malaysia. So for today I will be presenting about our assignment tool, which is for my part is about the hidden Markov model. So I will start off by briefing like what is the HMM, hidden Markov model. It is a mathematical model for statistics that is used to describe the evolution of observable events that depends on internal factors, which you cannot observe directly. So the interesting fact about HMM is that you don't know the probability of what is the outcome, but you know the outcome. So by doing that, you can actually train the algorithm for the hidden Markov model to predict the probability of that outcome happening. There's many transitions and many states, but then with a properly trained algorithm, you can properly predict the probability of the outcome because you already know the outcome. So before bioinformatics, HMM is actually used for speech, handwriting, and even gesture recognition. So it is a very good algorithm for, especially for speech algorithm. Like you would just like Stephen Hawking, how he's able to speak through the machine is actually using HMM algorithm. The algorithm can predict what his body is trying to say from his throat here. So right now, as I'm taking bioinformatics, this is the statistical approach for modeling biological sequences. This is because we are able to get the probability of the outcome of the biological sequences, such as the protein sequence or the DNA sequence. So there are a few tools here, as you can see in the poster. First is the hammer, HMMER, CHMM, and dimmer HMM. So these are the three main tools, but you will have to install it locally into your PC. So there are three algorithms used. First one is the maximum likelihood, second is the bound-merge algorithm, and the third one is the vertebrate training. So the first one, maximum likelihood, involves defining a likelihood function for calculating the conditional probability, meaning you will have to the algorithm will calculate the probability of the observing of the data sample given a distribution and the parameters. And the second one would be the bound-merge algorithm, which trains the HMM model by an observation sequence and generate a new hidden Markov model for detection. So this algorithm actually is used in attacking the firewall of a server. So meaning normally a hacker would use this algorithm, but for bioinformatics we are able to use it to generate a new HMM for the biological sequence detection. So the last one would be vertebrate algorithm, which is a dynamic programming algorithm for making inference based on the trained model and some observed data. So this one is more to the machine learning algorithm. So as you can see in figure 1, this is the basic example of the hammer tool. So the figure 1 shows the probabilistic parameters of a hidden Markov model. You have X as the state, Y as the possible observations, A as the state transition, meaning that how the parameters changes, meaning that the outcome changes also. So you will have B, the output probabilities. So by doing this, you can actually generate a lot of models based on a different outcome. So as figure 2, as shown in figure 2, this is about bioinformatics. You have this is a profile HMM modeling with it models a multiple sequence alignment MSA using hammer. So of course you start off with the multiple sequence alignment, and then the insertion and deletion mutation can be modeled because of course it's trying to predict the probability using the outcome. And the occupancy and amino acid frequency at each position is aligned in the alignment, which are then encoded, and the profile is created, meaning the HMM model is created for that sequence, for that MSA. So a profile HMM is a variant of HMM relating function specifically to biological sequence. So it turns MSA into a profile-specific scoring system. Just like I mentioned, it creates a model which is then used as a specific scoring system. So then you can align the sequences and search database for some homologous sequences, meaning you can search back the homologs of any proteins. So I would say, in conclusion, HMM can be improved. I noticed that it's not really improved. It's not being updated time to time. People are still using the very old algorithm, which is not it's not so effective. So I hope that HMM could be more efficient in the future. So thank you very much. I hope you like this video.